Okay, so good morning, everyone. Welcome to this seminar of the Institute of Physics in Opava. Today, it is my great pleasure to introduce Ioannis Gialamas. Ioannis was born in Athens, in Greece. He studied physics at the National and Kapodistrian University of Athens. He completed his PhD studies there in 2021, and since October of 2022, he has been working as a researcher in the National Institute of Chemical Physics and Biophysics in Tallinn, in Estonia. He has research interests that involve electroweak vacuum stability, primordial black holes, supergravity, gravitational dark matter, inflation, Palatini Formulation, scale invariant gravity. And today he will talk to us about quadratic gravity, inflation, and reheating in the Palatini Formulation. So, Yanni, whenever you're ready, you may start.
Okay, I'm ready. Thank you, Thomas, for the nice introduction. Hello, everyone. I would like to thank the organizers for this nice series of seminars, and of course, for giving me the opportunity to present my work. This talk is based on these papers, which were written in collaboration with Athanasios Lachanas, Alexandros Karam, Antonio Racciopi, Thomas Papas, and Vasilis Panos. These are the contents of my talk. I will start with a quick review of cosmic inflation, discussing some models. Then we will see how the inflationary observables are differentiated in metric and Palatini formulations of gravity, when the action contains non-minimal couplings and quadratic in the Ricci curvature terms. And having done all the groundwork, we will see how the Planck mass can be dynamically generated in scale invariant models with quadratic in curvature terms. Of course, feel free to interrupt me and ask questions during the talk. As you know, in physical cosmology, inflation is the theory of exponential expansion of space in the early universe. The inflationary epoch lasted from 10 to the minus 36 seconds after the Big Bang to about 10 to the minus 33 seconds after this Big Bang singularity. After the inflationary period, the universe continued to expand. Inflation also solves many other problems like the horizon, the flatness, and the magnetic monopoles problem. And also explains how the anisotropies observed in CMB are generated. And this, of course, the FRW metric we will use in our analysis. The simplest theory of inflation assumes the existence of one scalar field phi, which is minimally coupled to gravity and has a canonical kinetic term. A variation of the action with respect to the metric tensor G mu nu will give us the Einstein equations, from which we extract the so-called Friedmann equations, in which A is the scale factor that describes the expansion of space, and these rho and P are the energy density and pressure of the scalar field. The next step is to vary the action with respect to the scalar field phi, which will give us the known Klein-Gordon equation. Inflation is usually studied with the help of the so-called slow roll approximation. In this approximation, the scalar field rolls slowly to the minimum of the potential. The potential energy is much larger than the kinetic energy. And these two parameters, epsilon v and eta v, which are functions of the potential and its first and second derivative, have to be very small during inflation, which end approximately when one of these parameters becomes unity. Of course, the real end of inflation comes when the first slow roll parameter, Hubble slow roll parameter, sorry, epsilon1 becomes 1. As you can see from equation 6 here, as epsilon1 is smaller than unity, the acceleration of the scale factor, A2 dot, is positive, which means exponential expansion. In my analysis, we will see the condition, we will use, sorry, the condition epsilon v equals to 1 to determine the end of inflation in order to obtain analytic results. In this slide, you can see the various observables, which are the amplitude of the scalar power spectrum, AS, which depend on the potential, and the sorry, this is not this slide. Okay, which depends on the potential, and the epsilon v parameter, the spectral index NS, and the tensor to scalar ratio R. Don't forget that the parameters epsilon v and eta v are very small during inflation. Also, the variation of the scalar field during inflation is related to the so-called number of e-folds, n, which has to be between 50 and 60 for the horizon and flatness problems to be solved. These are the Planck 2018 data when combined with the bicep cake measurements. As you can see, simple models of inflation like quadratic or linear model of inflation are excluded from the current observations, while others famous models like the Starobinsky and Higgs inflation, these are not in this plot, but they are in this region, in the dark blue region, are well within the allowed region, of course. Now, let's have a look in popular models like the quadratic and the quartic model of inflation. The potential is given by equation 12, of course, where n equals 2 in quadratic inflation and n equals 4 in quartic inflation. In order to have analytic expressions, we compute the potential parameters epsilon v and eta v. And of course, the end of inflation comes in our analysis when the parameter epsilon v is 1. So we can compute the value of the field phi n at the end of inflation. This very simple formula. Then, using also the equation for the number of e-folds, we obtain these relations for the tensor to scalar ratio R and the spectral index NS. For 60 e-folds, as you can see, the spectral index NS is okay for the quadratic model, but the tensor to scalar ratio is much bigger than the observed value for both models. The current measurement is about, is smaller, the tensor to scalar ratio is smaller than 0.036. Another popular example is the Higgs inflation model, in which the Higgs field plays the role of the inflaton. And there is an extra non-minimal coupling between Higgs and gravity, this coupling here in the circle. Our aim is to move in the Einstein frame. So after a while rescaling of the metric and filter definition, in order to have a canonical scalar field, we arrive at the axiom 16, which is the Einstein frame axiom. In the small figure, in the insertion here, you can see the initial Higgs potential, while in the big one, you can see the inflationary potential, which is flat enough for large values of the field to drive spectral index and tensor scalar ratio in values that agree with the observations. Starobinsky inflation is perhaps one of the most successful and simplest models of inflation. In this case, an R-squared term is added in the usual Einstein-Hilbert action, and this parameter M capital is fixed from the value of the amplitude of the scalar power spectrum AS to be about 10 to the minus 5. Now, again, after a value scaling and a filter definition, the R-squared term is converted to a scalar degree of freedom with this famous potential, V, the Starobinsky potential. And the inflationary predictions are again, this is for 6 defaults, are again in good agreement with observational bounds. But there are actually two variational principles that one can apply to the Einstein-Hilbert action in order to derive the Einstein's equation. The standard metric variation, in which where the metric is the only dynamical degree of freedom, and the connection is the Levi-Civita, and the Palatini variation, where the metric is the only dynamical degree of freedom, and the connection, and one has to vary the action with respect to the metric and the connection in order to find the relation between the connection and the metric tensor. Considering the action of equation 20, where alpha of I is a non-minimal coupling, and varying with respect to gamma, to the connection, we obtain this equation for the connection, in which the first term, the circle term, is the Levi-Civita connection. And the second term arises only in the Palatini case. The omega is the logarithm of the square root of alpha A, whatever you want. And now, doing a value transformation, we obtain this action here in the Einstein frame, which of course is different in the metric and Palatini formulations. As you can see, the kinetic term is different. Of course, if there is no non-minimal coupling, like in GR, in general relativity, the two formulations are equivalent. Let's use this, let's see these differences in Higgs inflation, where the potential, as I said before, is the Higgs potential, and the function alpha of h is 1 plus xi h squared. After doing the value scaling and going to canonical fields, you can see that the field redefinitions are different in metric and Palatini formulations. And the same happens to the final potentials, as you can see from equations 24 and 25. Now, regarding the observables, the spectral index NS is the same in the two formulations, at least in first order expansion on the number of e-folds. And, but the tensor to scalar ratio is divided by xi in the Palatini case, being 10 to the minus 12 in contrast to the metric case, where it was here almost 10 to the minus 3, as you can see. The amplitude of the scalar power spectrum AS is also different, which, for example, for lambda, for the parameter lambda equals 10 to the minus 1, the parameter xi is 10 to the 4th in the metric, and 10 to the 8th in the Palatini formulation. Previously, we saw that when the action contains an R-squared term, this is transformed to a scalar degree of freedom in metric formulation. In the Palatini case, when the action contains an R-squared term in the Jordan frame, then in the Einstein frame, we have not an extra propagating degree of freedom, but we have a higher order kinetic term and more flat potential given by this equation here in the box. And as you can see, for large values of the, sorry, of the field, the potential V effective goes to a plateau 1/4 alpha, where this alpha is the coefficient of the R² term here. Finally, in these models, this is the Klein-Gordon equation, which is of course modified because of the higher order kinetic terms. And we have also a speed of sound which deviates from unity. Now, as for numerics, we have used the Hubble slow roll parameters epsilon1, epsilon2, and also the parameter S1, which is here in models with varying speed of sound. For the computation of AS, NS, and R, we have used this paper by Lawrence and others, in which they use a method called adiabatic approximation, and which is suitable for this kind of models with varying speed of sound. But after our numerical analysis, we saw that the higher order kinetic terms are negligible for all the models under consideration in the parameter space. In the left plot, you see the evolution of the scalar field for the range of interest. In the right plot, with red, is the epsilon1 parameter. Dotted black is the quantity that controls the contribution of the higher order kinetic terms. And as you can see, is at least 2 orders of magnitude smaller than unity during inflation. Only for some e-folds at the end of inflation can contribute a little bit. The blue line is the speed of sound squared, which is also very close to unity. Only in the end deviates, as you can see here, deviates a little from unity. This is for the quadratic model of inflation plus an R² term, but the same happens in the quartic or in other models. The number of e-folds at the scale k is the logarithm of the ratio of the scalar factor at the end of inflation over the scale factor at the scale k. It is given from this equation, in which T is the reheating temperature, H0 is the Hubble constant today, A0 the scale factor today, G and GS are the energy and entropy degrees of freedom, and W is the equation of state parameter, that is the ratio pressure over energy density. Let's see now how the quadratic and the quartic models are affected from the R² term. As I said before, we can discard the high order corrections in our analysis. We keep it in the numerics, but they are negligible. So in order to get analytical results, for the parameters we use, the epsilon v and theta v parameters, which now contain the non-minimal kinetic function, as you can see, is somehow, not non-minimal, the non-canonical function k, because the scalar field, let me see, so this is not canonical in this case. So we use these parameters epsilon v and theta v. The effective potential is of this form, with C being a combination of the parameter lambda and the parameter alpha. The amplitude is fixed to 2.1 times 10 to the minus 9 from observations. And so using these equations for the e-folds and the phi end, the value of the field and the end of inflation, we obtain a constraint on the quartic coupling lambda. Also, the parameter alpha is restricted to be larger than about 10 to the 8 in order to achieve the observational bound for the tensor to scalar ratio, R smaller than 0.036. For the quadratic model, V equals m squared over 2 times phi squared. The mass parameter m is constrained to be about 6.5 times 10 to the minus 6 to have an agreement with the power spectrum's amplitude. And the parameter alpha has to be bigger than about 10 to the 8 in order to have agreement, good agreement with the tensor scalar ratio constraint. In this plot, you can see the spectral index as a function of the reheating temperature for various values of the equation of state parameter. For W equals 1/3, we have the instantaneous reheating case, we will see below. And the spectral index is independent of the temperature, of the reheating temperature. The shaded regions in both plots correspond to the bounds from Planck. In these plots, we have used the alpha parameter to have these values. In this slide, again for the quadratic model plus an R squared term, you can see in the upper figures the number of E-folds as a function of the reheating temperature. Of course, again for W equals 1/3, the number of E-folds are specific. And in the lower, you see the amplitude of the scalar power spectrum AS, in which the yellow regions correspond to the acceptable range observationally. And the important is that all these lines can go up and down if we change the parameter lambda. Finally, for the quadratic model, this is the most important figure. As I said before, the spectral index was okay before the addition of the R squared term. But the tensor scalar ratio was not good. As you can see from this figure, as the parameter alpha gets larger, the tensor to scalar ratio decreases, and the curves enter again to the allowed region. The colors of the dots correspond to different temperatures, and the numbers in the dots correspond to the number of E-folds in each point. The situation in the quartic model is still not very good, because although for a lambda equal to about 10 to the minus 13, we have an agreement with the value of the amplitude of the scalar power spectrum, and for alpha bigger than 10 to the 8, we deal with the tensor scalar ratio. The value of the spectral index is still problematic. You can see that from these figures, in which all the curves are outside of the bounds. But if we go to a 2 sigma region, the line with W equals 1 barely manages to survive. But this is a particular case only. Now we will see how the quartic model can be rescued. This happens if we add a non-minimal coupling xi h square between gravity and matter. The observables and the parameters are given by these equations. And the important point is that the previous bad spectral index was in the quartic model 1 minus 3 over n. Okay, and now let me show you this in the quartic model. Okay, in this equation for n equals 6, the spectral index is 1 minus 3 over n, in which for this value it is 0.95, which is outside of the bounds. Okay, let me find the slide again. Okay, and now in our case, with this xi h squared term, it is 1 minus 2 over n minus a xi-dependent term. Xi cannot be as small as we want, and we found its marginal value is about 0.06 in order to have agreement at least with a few efforts between 52 and 60 efforts. And another remark is that for psi larger than 0.06, the parameter alpha is unbounded, since the right-hand side of this inequality is negative for this psi. For example, for psi equals 0.06, lambda of order 10 to the minus 12 and alpha 10 to 12, you see that the curves can be rendered in the allowed region. You can see this from the left figure. And of course, the same happens in the NSR plane, spectral index versus tensor to scalar ratio. As the parameter alpha gets bigger, the tensor scalar ratio is reduced. Now, given an inflationary model, the largest uncertainties in the number of efforts are mainly due to the period of universe reheat after its exit from inflation. The number of efforts during the reheating period are the logarithm of the ratio of the scale factor at the end of reheating over the scale factor at the end of inflation. In terms of delta N reheating, for given equation of state parameter, the reheating temperature is given by this equation. Since A reheating is bigger than A end, we have that the delta N reheating is bigger than 0 because W is bigger than -1. And so the reheating temperature is bounded from above. This bound is the so-called instantaneous reheating temperature, and the temperature gets this value if the number of efforts during reheating is 0, which means that A reheating, the scale factor at the end of reheating, is equal to the scale factor at the end of inflation. So the logarithm of 1 is 0, and delta N reheating is also 0. Okay. In the Higgs R-square model, we found that Higgs R-square means Higgs field plus non-minimal coupling plus an R-square term. We found that the energy density is given by this equation where f psi c is too complicated to be presented. So substituting this energy density to the previous equation here, we obtain this result for the instantaneous reheating temperature. Analytic results can be obtained only in the limits where the C parameter is much bigger and much bigger than psi square, or the C parameter is much smaller than psi square. In this plot, in the 6CI plane, we display the instantaneous reheating temperature as given by the equation we proved. For a number of efforts, if I remember well, is 55. Light colors correspond to larger temperature, of course, as you can see from the bar in the right. And the largest temperature, instantaneous reheating temperature, is 2.47 times 10 to the 15 GeV, which is within the yellow region near the value of the parameter psi 0.1 with this boundary, with boundary the blue dust line. In this paper, we consider a potential of this form, which contains a Ranic quartic coupling and a cosmological constant lambda capital, which adjusted so that the minimum of the potential is 0. Okay, phi is again non-minimally coupled to gravity. And the important here is that its vacuum expectation value can generate the Planck scale, as you can see. The vacuum expectation value is equal to m Planck over square root of xi. The minimization condition implies these two cases for the beta function and lambda, and the Corti coupling lambda. Now, expanding the Corti coupling around the vacuum expectation value and using the two possibilities for beta and lambda, we obtain these potentials, which we will call first order and second order potentials in these two limits, two cases. Okay. The first order potential in the Einstein frame has this form in equation 46. And for a vacuum expectation value much smaller than unity, it behaves like a linear potential, while in the opposite limit corresponds to a quadratic potential with this mass, mass m1. For the second order potential, when we go to the Einstein frame, the potential is completely quadratic with a different mass. Now, adding an R squared term in the action, where this alpha is dimensionless, we see that both potentials become flat, as you can see in the right plot, approaching the value 1 over 8 alpha. And these are the results for the tensor to scalar ratio, the spectral index, and the amplitude of the scalar power spectrum for the linear and linear in the left and the quadratic in the right limit. Finally, these are the predictions for the two models. For various values of the parameter alpha, as alpha becomes bigger, the tensor to scalar ratio decreases and decreases, and the models become again compatible with observations. For the first order model, the dashed lines correspond to small field inflation. That is, the inflation starts from field values smaller than the vacuum expectation value. And the solid ones are for large field inflation, which means that inflation starts from field values which are bigger than the vacuum expectation value. For the second order model, the predictions are just points, since it is pure quadratic, as I said before. In the right, you can see also the number of fifolds versus the tensor to scalar ratio for both models. Now, in this paper, in this model, we consider a U1 extension of the standard model, in which the extra particles are 3 right-handed neutrinos, 1 gauge boson, and a scalar field. These are the relevant Lagrangians, the Opava interactions, the scalar part, the standard model Lagrangian without a Higgs mass term, because it will be generated through this interaction term here, here, okay. And finally, this is the gravity Lagrangian, which contains, of course, the non-minimal couplings, an R square term, but now we have added also an R nu square term. And we will see its effect. The Planck scale is again dynamically generated through the vacuum expectation values of the scalar fields. Now we have 2 scalar fields, Higgs and one extra scalar field phi. The action in the Jordan frame is of this form, in which the scalar potential contains both the fields phi and Higgs. And before going to the Einstein frame, we will pass to an intermediate frame where we have only dropped the non-minimal coupling in front of the Ricci scalar, as you can see here. The R square term and the R mu square terms are still here. Usually this kind of models can be studied with the help of the so-called Gilden-Weinberg approach, in which we first find the flood direction of the tree-level potential, and then we compute the one-loop corrections. In equation 52, you can see the intermediate two-field potential. The flood direction is the direction in which the first derivatives of the potential are 0. And along the flood direction, the potential has this value given by equation 55. In this slide, you can see the mixing of the fields. Omega is the mixing angle, arctan to the ratio V, vacuum expectation value of H over vacuum expectation value of phi. M sigma and MS are the mass eigenvalues of the new fields. Along the flood direction, the field sigma vanishes, and the kinetic terms of the initial fields are written as a unique kinetic term for the new field S, which is a combination of the mixing angle and the non-minimal couplings xi phi and xi h. Finally, we perform the following field definition in order to render the kinetic term of S canonical. This is easy because this integration is very simple. Also, this parameter xi s is the effective non-minimal coupling constant, which is a combination of xi phi and xi h. This is the one-loop correction along the flood direction for the canonical field at some scale lambda capital. The important here is that this parameter m to the 4 that contains the masses of the standard model and the masses of the new particles must be positive defined in order to the one-loop potential to be bounded from below. For this reason, the difference 3 mx to the 4 minus 6 m neutrinos to the 4, these are the extra particles, must be bigger than about 300 GeV to the 4th. Now, after minimization of the potential, we can determine the scale lambda, and substituting it back to the potential, we obtain the one-loop correction along the flood direction. The final step is to get rid of the quadratic terms. So we write the intermediate frame action on this form, okay, where C is the curvature function that contains the R square and the R mu square terms. And LM, the LM here, is the matter Lagrangian for the canonical scalar field S. Introducing an auxiliary field sigma mu nu and defining the new variable q mu nu, the action takes this form, where the first term, q mu nu, r mu nu, is the usual Einstein-Hilbert term. Of course, for the new metric Q. And the rest part of the Lagrangian is the modified matter sector. This pinked part. Okay, now varying the previous action with respect to G mu nu will give us, and applying, sorry, a metric transformation, which is called now this formal transformation. We can solve G mu nu in terms of Q mu nu of the new metric and the scalar field and its derivative. This is a very lengthy calculation to be presented, so let's see only some details on this. This is the disformal transformation, in which the first part is just the usual conformal transformation, and the second part contains derivatives of the scalar field. In the bullets, you see the inverse metric Q mu nu, the determinant of the metric, the kinetic term in terms of the new metric Q, and the kinetic term in terms of the old metric G. Substituting now all of this in the variation of action I showed you before in this equation, and requiring that the coefficients of Q mu nu and d mu nu s, d nu s canonical must vanish, we obtain these equations, 68 and 69. And to solve this for the variables alpha and beta, we assume that in slow roll can be written as a series expansion in terms of the kinetic term. So substituting these expressions for alpha and b back to the equations 68 and 69, we can determine the coefficients A0, B0, etc. This new parameter, alpha tilde, is a combination of the coefficient alpha of the R squared term and the coefficient beta of the R mu nu squared term. This is the final Einstein frame action, where we have omitted the higher order kinetic terms because they are negligible. The inflationary potential has this form, which is the same with the one obtained by the pure R squared term. The only difference in this model is that in this case, there is a full series of higher order kinetic terms, and not only one as in the R squared term. In this figure, you see the initial two-field potential. The cyan line is the flat direction. The red one is the full one-loop effective potential. Full one-loop means three-level plus one-loop correction. And the green is the inflationary potential, after, of course, the effect of the higher curvature terms. Here, it is the same potential, the green line here. And as you can see, increasing the parameter alpha tilde, the potential becomes flatter. And for very big values, it is also symmetric. So the prediction of small field inflation and large field inflation, that means inflation from the left side and from the right side of the vacuum expectation value, the predictions are expected to be the same. In this slide, there are some limits for the inflationary observables. For small psi s, and alpha tilde 0, both small field inflation and large field inflation give quadratic predictions. In the other limit, the spectral index is quadratic, but the tensor to scalar ratio is quartic, but the tensor to scalar ratio can be quartic or 0 for large field inflation and small field inflation, respectively. Now, when alpha tilde is not 0, we have the usual effect. The tensor-to-scala ratio gets modified as it is displayed here, and becomes smaller as the alpha tilde parameter becomes larger. These are the observables in the NSR plane. The right panel is just is the same but in logarithmic scale. The black dots correspond to the xi-s goes to 0, 0 limit. The upper parts of the curves correspond to large field inflation and the lower parts to small field inflation. In this table, you can see some values for the observables. And finally, we saw that for viable inflation, the xi-s must be smaller than 4 times 10 to the minus 3. So the vacuum expectation value for S, for the field S, is bigger than 15 Planck masses. And also here, you see the parameter m to the 4, which was, let me show you this again. It was this parameter here, okay, in the one loop effective potential. Okay, this parameter is constrained from the amplitude of the scalar power spectrum, and the constraint for xi-s, as I said before, it is smaller than 4 times 10 to the minus 3. So m to the 4 is bigger than about 10 to the minus 6. To sum up, in metric formulation, one scalar field plus r squared term leads to 2 field inflation, while in the Palatini case, leads to one field inflation with high order kinetic terms and an asymptotically flat potential. This flatness reduces the tensor-to-scala ratio, but the amplitude of the scalar power spectrum and the spectral index remain unaffected, at least at first order in an expansion of E-folds. Also, we saw that the Planck scale can be dynamically generated via the vacuum expectation values of the scalar fields when we have one or more scalar fields. Thank you very much.